there! In today's lecture, we'll define the security notion for public key encryption schemes. We will motivate the definition by describing two attacks on the basic RSA encryption scheme, dictionary attacks and Chosen-ciphertext attacks. We will then present RSA-OAEP, a variant of the basic RSA encryption scheme that is secure with respect to our strong notion of security.
I'll remind you that Alice's RSA public key is a pair of numbers n and e, where n is the RSA modulus and e is Alice's encryption exponent. Alice's private key is the decryption exponent d. E and d are related by the congruence e times d congruent to 1 modulo phi, where phi is defined to be p-1 times q-1. In basic RSA encryption, a plaintext m, which is a number between 0 and n-1, is encrypted by raising it to the power of e modulo n. The ciphertext C is decrypted by raising C to the power of Alice's decryption exponent d modulo n. Let's first consider security of the RSA key generation procedure. I'll note that if an adversary can efficiently factor n, then she can compute phi of n, and thereafter compute d just as Alice did. In fact, it's been proven that any efficient method for computing the private key from the public key is equivalent to factoring n. So, as long as factoring n remains difficult, no one can compute Alice's private key from Alice's public key. Thus, hardness of factoring n is a necessary and sufficient condition for the security of RSA key generation. Let's now consider security of the basic RSA encryption scheme. A basic notion of security is that it should be computationally infeasible to compute the plaintext from the ciphertext. This is known as the RSA problem, defined as follows. Given an RSA public key NE, and given a ciphertext C, which is the encryption of some unknown plaintext M, the problem asks to determine the plaintext M. In other words, the RSA problem is a problem of computing the unique ETH root of C modulo n. The only effective method known for solving the RSA problem is to factor n. Once you have the prime factors p and q of n, you can compute phi of n, and thereafter compute d. Once you have d, you can find the ETH root of C modulo n by raising C to the power d modulo n. Henceforth, we will assume that the RSA problem is intractable. I want to emphasize that this is a new assumption. We need factoring to be hard. Otherwise, one can efficiently find the RSA private key from the public key. However, it's still possible that factoring is hard, but the RSA problem is easy. Hence, intractability of the RSA problem is a new assumption. I'll next describe two attacks on the basic RSA encryption scheme. The first attack is a dictionary attack. Suppose that in an application, the plaintext is chosen from a relatively small and known set M of messages. For instance, if Bob is encrypting stock recommendations for Alice, then one can predict that the set M contains messages such as buy 100 IBM stock or sell 100 IBM stock. Suppose that Bob encrypts such a plaintext M for Alice, and the adversary captures the corresponding ciphertext C. The adversary can then encrypt each message in the known set of messages until C is obtained. This works because RSA encryption is a public operation which depends only on Alice's public key. Moreover, encryption is a deterministic process, so when Eve encrypts the plaintext M, she gets the same ciphertext C as Bob obtained. A countermeasure to dictionary attacks is to append a randomly selected string of sufficient length, for example 128 bits, to the plaintext M prior to encryption. This string is called a salt. The salt is appended to the plaintext, and the salted plaintext is what is encrypted with RSA. Note that a plaintext M can now be encrypted to one of 2 to the 128 possible ciphertexts, one for each possible salt. So, when the adversary sees a ciphertext C and suspects that it corresponds to a plaintext M, to test her hypothesis, she needs to encrypt M with each of the possible salts and check if she gets C. But this isn't feasible because there are too many salts to try. The second attack on basic RSA encryption is a Chosen-ciphertext attack. Suppose that the adversary Eve has a target ciphertext C that Bob encrypted for Alice. Suppose also that Eve can somehow induce Alice to decrypt any ciphertext for Eve, except for C itself. I'll say that Eve has access to a decryption oracle. Eve can decrypt C as follows. Eve first selects an arbitrary number x between 2 and n-1 that is coprime with n. She computes C hat by multiplying C with x to the power e modulo n, where ne is Alice's public key. I'll note that C hat is not equal to C unless C and n are not coprime. Indeed, if C and n are not coprime, then Eve could compute the GCD of C and n, which would be a prime factor of n. In this way, Eve would totally break the RSA encryption scheme. So we'll assume that C and n are coprime, and so C hat is not equal to C. Eve then obtains the decryption M hat of C hat from the decryption oracle. Let's note that the decryption oracle computes M hat by raising C hat to the power d modulo n. Now, C hat by definition is C times x to the power e modulo n. Expanding and then replacing C to the d by m and x to the ed by x gives m times x modulo n. Then Eve can compute m by multiplying m hat by x inverse modulo n. Note that x inverse mod n exists since x and n are coprime.
You might object that a Chosen-ciphertext attack is very artificial. The adversary can obtain the decryption of any ciphertext of her choosing, except for the challenged ciphertext C itself. And indeed, this is a very strong attack. However, if we can design encryption schemes that resist even this very strong attack, then we're guaranteed resistance to weaker kinds of attacks that might be realistic in practice. We'll give you an example of such an attack in the second part of this course on cryptographic deployments. So, henceforth, we'll demand that public key encryption schemes be resistant to Chosen-ciphertext attacks.
A countermeasure to circumvent Chosen-ciphertext attacks is to add some prescribed formatting to the plaintext prior to encryption. After decrypting the ciphertext C, if the plaintext is not properly formatted, then Alice would reject C, and so the decryption oracle available to the adversary does not return a plaintext. The rationale for the formatting is that when Eve modifies C by multiplying it by x to the power of e modulo n, the decryption of C hat, namely M hat, is the original plaintext, which is properly formatted, times x modulo n. The hope is that multiplying m by x modulo n results in a plaintext that is not properly formatted, and so Alice would reject m hat and not return m hat to the adversary. In summary, RSA encryption should include salting and formatting. Let's formulate a security definition for public key encryption. Like all our security definitions, we want to give the adversary the strongest possible capabilities and make her goal as weak as possible. So we'll give Eve access to a decryption oracle and only demand that she break semantic security, namely, that she learns something about the plaintext from the ciphertext, other than the length of the plaintext. We'll say that a public key encryption scheme is secure if it is semantically secure against Chosen-ciphertext attack by a computationally bounded adversary. To break a public key encryption scheme, Eve should accomplish the following. Eve is given a challenge ciphertext C encrypted for Alice. She's also given Alice's public key NE. Eve has access to a decryption oracle to which she can present any ciphertext of her choosing for decryption except for C itself. After a feasible amount of computation, Eve should learn something about the plaintext that corresponds to the challenge ciphertext C other than the length of the plaintext. Here is one variant of the basic RSA encryption scheme that meets our strong notion of security. This is the RSA Optimal Asymmetric Encryption Padding Scheme, or RSA-OAEP. I'll need some notation. Let k be the bit length of n. For example, k might be 3072. Let L be k minus 256 minus 1. I'll assume that M, the plaintext, has bit length L minus 256. If M is smaller, then it could be padded in some way to get a string of length exactly L minus 256. R will denote a randomly selected 256-bit salt. G1 and G2 are so-called masking functions. G1 maps bit strings of length 256 to bit strings of length L, whereas G2 maps bit strings of length L to bit strings of length 256. In practice, G1 and G2 can be built from a hash function such as SHA-256. For instance, G1 of R could be defined to be the hash of 0 appended to R, concatenated with the hash of a 1 appended to R, concatenated with the hash of 2 appended to R, and so on. One would continue hashing the counter with R until you get a total of L bits. The rationale is that since SHA-256 behaves like a random function, we can treat the output of G1 as a random bit string. Similarly, G2 of R could be defined to be the SHA-256 hash of R. Now, to encrypt the plaintext M, first select a salt R and append to its left the plaintext M and 256 0 bits followed by a single 0 bit. Note that the resulting bit string has length exactly k bits. The leftmost 0 bit ensures that the integer is less than the modulus n, which is k bits long. The string of 256 0 bits serves as formatting for M. The string R serves as a salt. Next, G1 of R is computed and the resulting bit string of length L bits is added to the formatted M to get an L bit string, which I'm calling S. So S is a masking of the formatted plaintext by G1 of R. Then G2 is applied to the string S, and the resulting bit string is added to R to get the bit string T of length 256 bits. So T is obtained by masking R with G2 of S. Let's call the resulting bit string M. M has bit length K. Lastly, M is encrypted using the RSA encryption function by raising it to the power E modulo n to get the ciphertext C. In summary, R serves as the salt, and the 0 string serves as formatting. The formatted plaintext is masked by G1 of R, and the salt is masked with G2 of S. The resulting string M is then encrypted using basic RSA encryption. Here is the decryption procedure for RSA-OAEP. To decrypt the ciphertext C, Alice does the following. She first raises C to the power of her private key D modulo n to get the formatted plaintext M. And she represents M as a binary string of length k bits. Recall that k is the bit length of the modulus n. She then parses m into a single bit, followed by L bits, which she calls S, and the last 256 bits, which she calls T. She checks that the first bit is 0. If not, then she rejects C. Alice then computes R as G2 of S plus T, and she computes G1 of R plus S. This is a bit string of length L bits, which she parses into A and B. A has bit length 256, and B has bit length L minus 256. Finally, if A is a 0-bit string, then she outputs B as a plaintext. Otherwise, the plaintext was not properly formatted, and she rejects C.
You can check that, if C is a valid encryption of a plaintext capital M, then the decryption algorithm will accept C and output the plaintext capital M. In other words, RSA-OAEP decryption works.
RSA-OAEP comes with a very nice security guarantee. We have the following theorem. Suppose that the RSA problem is intractable. Suppose also that the masking functions G1 and G2 are random functions. Then RSA-OAEP is a secure public key encryption scheme. As with all our security theorems, the conclusion is very appealing. Namely, we have a mathematical guarantee that RSA-OAEP is semantically secure even against Chosen-ciphertext attacks. But, as with all our security theorems, this conclusion has some conditions. The first hypothesis is that the RSA problem is intractable. This hypothesis is unavoidable for RSA security, because if the RSA problem were easy, then one could always decrypt C to get M, and then recover the RSA plaintext capital M. So this condition is necessary for RSA encryption to be secure. The second assumption, that the masking functions are random functions, is a very strong assumption. Indeed, in practice, G1 and G2 are constructed from hash functions such as SHA-256. These hash functions behave like random functions, but are not random functions. So even though G1 and G2 behave like random functions, they are not random functions. Hence, the theorem is a highly conditional guarantee of security for RSA-OAEP. A key encapsulation mechanism, or KEM, is a key establishment protocol that allows two parties to establish a shared secret key. This key is called a session key. A KEM is comprised of three algorithms. A key generation algorithm that Alice uses to generate an encapsulation key and a corresponding decapsulation key. The encapsulation key is Alice's public key, whereas the decapsulation key is her private key. Bob uses the encapsulation algorithm to generate the secret key and ciphertext using Alice's encapsulation key. He sends the ciphertext to Alice. Alice uses the decapsulation algorithm with the decapsulation key to recover the secret key from the ciphertext. RSA-KEM is a conceptually simple key encapsulation mechanism that avoids the complications with padding that we saw in RSA-OAEP. A party Bob can use RSA-KEM to transport a session key K to Alice, and thereafter, Alice and Bob can use the session key K to encrypt and decrypt messages for each other using AES-GCM. Key generation for RSA-KEM is the usual RSA key generation. To encapsulate a key for Alice, Bob does the following. He obtains an authenticated copy of Alice's encapsulation key NE. Then he selects a random integer R between 0 and n-1 and encrypts R by computing R to the power E modulo n. He also computes K by applying a key derivation function KDF to R. He sends C to Alice. To recover the session key K, Alice decrypts C by computing C to the power D modulo n to get R. And then she applies the KDF to R to obtain K.
The next 2 video lectures will be devoted to a study of the RSA signature scheme. Have a great day.